All right. Thank you for the introduction, Julian. For those of you I haven't met, my name is Nick Stone. I'm an Einstein Fellow at Columbia University, and as Julian mentioned, I'll be discussing some theoretical rate calculations I've done for figuring out how often stars are tidally disrupted in realistic galactic nuclei. And one thing I want to try to focus on in my talk is how we can compare these theoretical rate estimates to observationally inferred ones. So we've already heard a lot about TDs. I won't belabor this with a long introduction about what they are, but I want to jump right to what was found by Brian Metzger and myself in a paper we wrote at the end of last year, which I think could be called a missing flare problem. So the gist of this is that we performed a theoretical rate calculation that took a large empirical sample of about 150 nearby galaxies and computed the rates at which stars are driven into the tidal radius by two-body relaxation off of other stars. And one of our primary findings was that there seems to be a large discrepancy between our theoretical event rates, which predict a disruption rate of, at the very least, 10 to the minus 4 stars per galaxy per year, and perhaps an order of magnitude higher, and the observationally inferred event rates, which have some range of uncertainty, but I would say the most robust estimates tend to find rates of the order 10 to the minus 5 stars per galaxy per year. So I'll walk through the mechanics of what we did to get this theoretical rate, and then discuss some possible resolutions and why none of them are ultimately completely satisfying. And then at the very end of this talk, I'll shift from my paper with Brian to some ongoing work I have with Short van Velzen, discussing this seeming puzzle concerning E plus A or perhaps post-starburst galaxies and why TDEs seem to prefer to live in these. And some preliminary evidence that we've gathered may argue against one theoretical explanation for this preference. So to begin, I'll start with a general introduction to the theory of two-body relaxation and how stars are actually tidally disrupted. And the way to think of this is in terms of a phase space loss cone in the centers of galaxies. So in your distant galactic nucleus, you have a supermassive black hole, this black dot here, and it has some tidal disruption radius around it, this shaded disk right here. So if you think about the stars orbiting the black hole, and you focus on one star in particular, there's a conical region in that star's velocity space, which, if the star happens to enter it, it will correspond to the end of the star's life. So if the star's velocity vector falls inside this cone here, the so-called loss cone, then upon completion of an orbit, its pericenter will pass within the tidal radius, and the star will be disrupted. If you're thinking about an idealized galactic nucleus that's spherically symmetric, you can write down this loss cone as a condition on specific orbital angular momentum, J. And in particular, if your specific orbital angular momentum falls below a critical value, that's the square root of g times black hole mass times the tidal radius, and there's a missing factor of 2 in there, sorry, then the star will be destroyed upon its pericenter passage. So near the black hole, the loss cone is generally empty, and the rate of tidal disruption is set by the rate at which relaxational processes scatter stars into it, the rate at which relaxational processes diffuse stars through phase space. Now, the most ubiquitous and theoretically robust of these processes is two-body relaxation, uncorrelated scatterings of stars off of each other. We might hear about some more exotic forms of relaxation in the next talk from Tal, but the general point I want to make is that these alternative relaxational mechanisms only increase the rate of stellar tidal disruptions. And the reason I'm going to neglect them for the remainder of my talk is that, as I said a slide ago, a primary motivation for what I'm doing here is seeing if anything can be done to address this discrepancy between theoretical event rates, which are too high, and observed ones, which are too low. So one goal that Brian and I had was to just vary as much as we could with the standard theory of two-body relaxation and see if we could beat down these theoretical rates into agreement with the observed ones. A secondary motivation for all of this is to try to understand how well statistical samples of tidal disruption flares will probe the demographics of low-mass supermassive black holes that are otherwise hard to study. So to walk through very quickly the calculation that Brian and I have done, what we did was we took a large sample of nearby galaxies, roughly 150, that had high-resolution Hubble photometry and had been fit to parametrized surface brightness profiles. So we take this sample of galaxies, we estimate black hole masses through scaling relations, generally m sigma, and then we apply the semi-analytic formalism developed by McGoyan and Tremaine and then Wang and Merritt to calculate the event rate due to two-body relaxation. So the first step is to take your observed surface brightness profile and deproject it. If you assume spherical symmetry, then this can be done with a simple Abel inversion, and that gives you a 3D density profile, rho of r. Then, if you further assume an isotropic velocity field, you can compute a distribution function of stars in energy space, f of epsilon, where epsilon is specific orbital energy. I've made a couple of assumptions here, and I'm going to come back to the importance of those later in this talk. But if we take this distribution function for the time being, we can simply compute orbit average diffusion coefficients due to two-body relaxation. So you can calculate these diffusion coefficients to tell you how quickly stars move through energy space or angular momentum space. It turns out that diffusion in angular momentum space is the more critical thing here in terms of setting the actual rate of two-body relaxation. So we compute the orbit averaged angular momentum diffusion coefficients, and then that gives us the flux of stars into the loss cone from every bin of orbital energy, and that's what's shown in this plot right here. So in this plot, we have two nearby galaxies, a cuspy galaxy in green and a more core-like galaxy in orange. Those adjectives refer to the steepness of the slope of the central stellar density profile. So what you can see is that the green cuspy galaxy has a significantly higher rate of tidal disruptions. Maybe you can't see it, the text is a little small, but if you integrate this loss curve over energy space, the rate of tidal disruptions in the cusp galaxy is about an order of magnitude greater than that in the core galaxy, and that's a very representative qualitative conclusion. So there are a number of smaller details that go into this that I don't have time to discuss in great depth here, but if you're curious, you can do things like vary your choice of parametrization, vary your choice of present-day stellar mass function, vary a few other parameters also, like the scaling relations you use for computing black hole mass. None of these things seem to affect our results very much. Here are our results. So what you can see here is a scatter plot of all 150 galaxies in our sample, showing the rate of tidal disruptions per galaxy per year versus the black hole mass of the galaxy. And there are a few salient things to take away from this plot. One is that there's a reasonable amount of scatter. Another is that the cusp galaxies, those with steep central density profiles, seem to have significantly higher TDE rates than the core galaxies, which are labeled in red right here. So these lines are power law best fits to the cusp subpopulation, the core subpopulation, and the total galaxy sample, the black line. The reason that the total galaxy sample seems to obey a steeper power law is because of this secular trend, where as you go from high mass galaxies to low mass ones, you tend to shift from more core-dominated profiles to more cuspy ones. So the general takeaway from this is that the highest disruption rates are preferentially in smaller cuspy galaxies. One side note that I was going to leave out of this talk, but I think is actually very relevant given a lot of the talks we heard yesterday, is that there are actually two different regimes of tidal disruption, and they can be parametrized by this dimensionless number q, which can be thought of as a ratio of the per orbit perturbation to your angular momentum divided by the critical angular momentum of a loss cone orbit, and then squared. And if q is a number much less than 1, then you're in the so-called diffusive regime, where you're taking very small steps in your random walk through phase space, and you very gently diffuse into the loss cone. And in this regime, almost all tidal disruption events are grazing ones, where this beta parameter we've been hearing a lot about, the ratio of tidal radius to pericenter, is roughly equal to 1. But in the opposite regime, where q is much greater than 1, you're taking very big steps in your random walk through phase space, and the loss cone appears like a very small pinhole target that you're bouncing across. So stars in this regime, which are preferentially further away from the black hole, can actually sample a wide range of beta. So if you're a theorist or an observer who's interested in what happens in these more extreme high beta events, one, I think, reassuring qualitative finding from our work is that if you plot the fraction of TDs from the pinhole regime as a function of black hole mass, you find that that fraction is highest for low mass galaxies that dominate the volumetric event rate. So the low mass galaxies that source most TDEs are preferentially in the pinhole regime. One kind of interesting qualitative fact that I don't have a great physical explanation for is that at any given bin of black hole mass, core galaxies are more pinhole-ish than cusp galaxies are.
How is this
Yeah.
related to full and empty loss cone?
Yeah, great question. So the pinhole regime is basically the full loss cone regime. The diffusive regime is basically the empty loss cone.
Is it the usual trend of your collaborators to reinvent names for known phenomena?
No.
Oh, well,
Existed a long time ago as well.
I'll let Tal come to my defense here. Yeah, so I think these terms were first invented by Cohn and Kulsrud in '79, but
Full and empty loss cone was invented by Hill in 75.
okay. Well, both this term is a little more colorful. I like it for that reason. Both are very equivalent. Yes, Ram?
largely accepted, that even in the diffusive regime, you
Mhm.
find that quite a few beta lower than 1 tidal disruption events will occur
Or higher than one, you mean? Or,
in both regimes.
okay.
Definitely when the loss cone is full, then the scaling is beta to the minus 1.
Yeah.
Even in the empty loss cone, where you would think everything comes just from diffusion to the edge of the loss cone, you will find because the scattering, the diffusion coefficient when you calculate it, has equal contribution from scattering in all scales. The large scale scattering will populate the inner side of the loss cone, and the actual scaling will not be so different from the beta to the minus 1 that you get in the full loss cone up to some logarithmic factor. So it's actually a smaller change than.
So you're right that this is definitely a qualitative simplification, and for people who are interested in the more detailed delineation between these regimes, I'd recommend Linda Strube's unpublished PhD thesis. There's a chapter that was never published as a paper, but that goes into great detail about this. You can find it on ADS. And what she finds is basically what you're saying, that in the diffusive regime, there's this logarithmic suppression of high beta events. So the beta equals 1 events dominate by some factor that's generally pretty large, and then you get into a sort of power law scaling with beta. But I think to leading order, most events are beta equals 1 in the diffusive regime.
Following up on that, how fuzzy is the boundary between simple and diffusive? Like, when does it transition from beta exactly minus 1 to something less than that?
Yeah, that's another good question. Linda's thesis goes into great detail about this. Roughly speaking, you start seeing large suppressions in high beta events at Q of 0.3. That's the approximate separation. Okay, yeah, this is super interesting from a theoretical perspective, but I want to get a little more into the observations. So please feel free to ask questions about this afterwards if you're curious. So, okay, we have this power law best fit for how tidal disruption event rates depend on black hole or galaxy mass. If we want to turn this into a volumetric or per galaxy rate, we need to convolve it with a Schechter function that tells you how common galaxies of different masses are in the local universe, but we also need to say something about the occupation fraction of small supermassive black holes, because this is something that's not very well understood. And in light of our ignorance, we parametrize it, we consider different ad hoc occupation fractions for low mass black holes. Our most conservative case is this gray line where the occupation fraction turns over at about 10 to the 6.5 solar masses. Arguably, this is ruled out by current observations, but we include it for completeness and for conservativeness. So here's what you get when you convolve all of those things. This is the volumetric event rate, number of tidal disruptions per cubic megaparsec per year. Each curve, corresponding to a different assumption about occupation fraction, is also labeled with the per galaxy event rate. And so you can see that even in our most conservative assumption about black hole occupation fraction, we still get an event rate that's 2 times 10 to the minus 4 per galaxy per year, an order of magnitude higher than typical observational estimates. And in what I would say is a more realistic assumption about occupation fraction, we get between 4 times 10 to the minus 4 to 1 times 10 to the minus 3. Oh, sorry. So the occupation fraction is just what was shown in this plot right here. It shows the fraction of galaxies that actually have black holes with the mass that you would infer from m sigma. So it asymptotes to unity as you get to high black hole masses, where we know that most galaxies have black holes, and then it turns over at some arbitrarily chosen low mass.
Do you assume that all of those low-mass black holes have steep cusps around them?
That is an implicit assumption by using our.
We know that M32 is really unusual.
I think that is an implicit assumption by our extrapolation of the power law best fit of our sample down to smaller galaxy masses. That is an important assumption, but I would like to point out that it's justified for this curve and arguably this curve as well. Yeah. Okay, so where does this leave us? We've seen that this rate discrepancy is very persistent. We've varied a lot of things. We've tried to make our calculation as conservative as possible. In particular, we've only considered two-body relaxation and spherically symmetric galactic nuclei. Our assumption of spherical symmetry is potentially underestimating the event rate by a factor of a few to an order of magnitude if you have triaxial nuclei. How can we resolve this discrepancy? Well, I think I've shown that it's not occupation fraction. Even an unrealistically conservative choice. How much time do I have left, Julia? Great. Okay. So even an unrealistically conservative choice of occupation fraction still leaves you with an event rate of 2 times 10 to the minus 4 per galaxy per year. I think that observations of nearby nuclear star clusters where you can put stars on the Hertzsprung-Russell diagram without enormous reddening hint that the answer is not dust obscuration hiding 90% of TDEs. I'm not an expert in this, though, so I'm very open to different opinions from observers. Relatedly, it could be observational selection effects. So backing out an observationally inferred event rate from our current TDE samples, which are limited in number and also highly inhomogeneous, it's a tricky business, and different selection effects often go into this. But I would incline towards saying it's not just selection effects, based on the work of Short Van Velzen and Glennis Farrer last year, which took a flux-complete sample of SDSS-selected TDEs and found just about the lowest observationally inferred event rate out there, 1 times 10 to the minus 5 events per year. But as we've already heard in this conference from both Thomas and Peter Maxim, it's possible that there's some wiggle room in these estimates. I would say that it's also probably not exotic stellar dynamics. So the one non-conservative assumption we made in all of our modeling was the assumption of isotropic velocities in the stars in the galactic nucleus. If, in particular, you have anisotropic velocities with a strong tangential bias, that can beat down tidal disruption rates by potentially orders of magnitude. And that seems at first glance like a pretty tempting possibility, which is why Brian and I floated it in our paper. But very nice follow-up work by Kirill Lezhinin and Eugene Vasilyev seems to indicate that this is not actually a solution, because galactic nuclei can't naturally sustain a strong tangential anisotropy for a Hubble time, at least in the small galaxies that seem to dominate the volumetric event rate. So these small galaxies want to relax to a more isotropic velocity field where our rate calculation would be accurate. So I think the only way for this kind of exotic dynamical process to push down the TDE rate is if there's some ubiquitous feature of small galactic nuclei that cranks up tangential anisotropies over time. What would cause that is very non-obvious to me, but if theorists in the room have ideas, I'm open to them. So ultimately, the solution I'm leaning towards, which I think flows perhaps naturally from a lot of the discussions earlier in this conference, is that there's a strong bimodality in optical and perhaps X-ray emission also in tidal disruption events, with a large majority of events unable to produce the bright flares that are harvested in our current observational samples. There are probably a few different ways to get this kind of bimodality, but one that's been hinted at earlier in this conference is a strong variation in circularization efficiency. So I think, as I mentioned in a comment in Jane Dye's talk yesterday, we already see a suggestive hint of this if you make a histogram of black hole masses calculated from galaxy scaling relations, so there's some uncertainty here, but if you make this histogram for the black hole masses in our current sample of tidal disruption flares, and I would call attention in particular to this prominent bump in the UV and optically selected sample, not at the 10 to the 6 or 10 to the 5 solar masses suggested by the theoretical work I showed you a few slides earlier, but instead at 10 to the 6.8 solar masses. And just to put some numbers in for context here, if you take the 0.3 solar mass stars that dominate the disruption rate for a Krupa IMF, and you take a 10 to the 6.8 solar mass black hole, your tidal radius is at 8 gravitational radii, and your stream self-intersection radius is at 90 gravitational radii. So perhaps for black holes being disrupted by for stars being disrupted by black holes this large, we're in a regime of efficient circularization, and below this, we're in a regime closer to what's seen in the simulations of Shiokawa et al. Of very inefficient circularization due to large self-intersection radii. But ultimately, even this isn't a totally satisfying explanation for this rates discrepancy. So Brian and I have redone our volumetric rate calculation, putting what I think is a fairly strict cut on pericenter, saying you need pericenters less than 12 Rg in order to produce a luminous flare. And while that really does push down some of these more extreme event rates that you get from more liberal occupation fractions, it doesn't do very much at all to the more conservative event rates, which are still of the order a few times 10 to the minus 4 per galaxy per year. That's what I have to say about tidal disruption event rates in general. I'll now very quickly discuss some preliminary results from a work in progress with Short Van Velzen concerning this preference that TDEs have for E+As or perhaps post-starburst galaxies. There are a number of different hypotheses theorists have come up with to explain this. Some are very exciting, like binary supermassive black holes, nuclear triaxiality, or an idea that Brian and I floated in our paper last year, which is just that maybe it's natural to expect a very overdense nuclear star cluster to be generated in the starburst that gives these galaxies their characteristic spectral lines. And fortunately, this last hypothesis is something that in principle can be tested on a small sample of nearby E plus A galaxies by running the machinery by running the two-body rate calculation machinery I've already described. One such galaxy is the conveniently nearby one, NGC 3156, and I'll show you results for this today. So NGC 3156 is in many ways an optimal target for this kind of study. It's only 22 megaparsecs away, and it has an inferred black hole mass of 1 times 10 to the 7 solar masses. So the radius of influence is almost resolvable with high-resolution Hubble photometry. And in fact, archival HST observations already exist for this galaxy, and were fitted to a nuclear surface brightness profile by Atlas 3D. So if you look at the Atlas 3D paper, you see that NGC 3156 is actually an extreme outlier in the steepness of its central profile. The surface brightness profile goes as r to the minus 1.8, which is enormously higher than any of the 150 galaxies Brian and I looked at in our sample. There, the steepest central surface brightness profiles went as r to the minus 1.1. But what you can see, so at first glance, it seems like this galaxy should be a tidal disruption event factory, but if you look at the details of this fit, and in particular this residual plot here, you see that it very poorly fits the innermost pixels, overpredicting the central light by a large amount. So in fact, what this tells us is that there is a turnover in the density profile right at the radius, or very close to the radius of influence. And what Short and I have done is a more careful PSF deconvolution. We find that the surface brightness profile breaks to a shallower, but still cuspy, r to the minus 1 at about 20 parsecs. So here's my final slide. When you take a more realistic fit that eliminates those central residuals, you find that NGC 3156 is an utterly unexceptional galaxy in its central mass density and in its TDE rate, which is roughly 1 times 10 to the minus 4 per year, due to a combination of this turnover and a low mass to light ratio, which follows from its very young stellar population. So this is only one galaxy. We're hoping to follow this up with similar calculations in more nearby E plus A's, but this provides at least suggestive preliminary evidence that the preference TDEs have for E plus A hosts is not due to central stellar overdensities, and maybe is related to something more exotic like nuclear triaxiality or binary black holes. Here's a summary of my conclusions, and I'll take any questions you have right now.
Two questions. The first is, what is the main difference between your calculations and earlier theoretical estimates, which were lowered by at least an order of magnitude?
So
This is the first question.
okay.
And the second question is, you referred to the E plus A anomaly or effect. If you take it as a fact, then this even increases the discrepancy between the observed rate in field galaxy and the theoretical rate that you estimate, because this would imply that if half of the event rate that we have seen are in E plus A, that the effect in an average galaxy is smaller than factor of 2 or something like that.
Mhm.
This makes the discrepancy even larger.
Yeah, so regarding your second question, I totally agree with that. If 50% of TDEs are coming from E plus A galaxies, that makes this rate discrepancy a factor of 2 worse in non-E plus A's. Regarding your first question, I would actually dispute that previous work along these lines found significantly lower event rates. So the 1999 paper by Megorian and Tremaine did, because they were using an incorrect M-sigma relation. The 2004 paper by Wang and Merritt actually found results pretty in line with ours by shifting to a more modern M-sigma relation that doesn't differ strongly from what we used. The difference is that they didn't emphasize this discrepancy for 2 reasons. One is that there had been many fewer observed TDEs found, so it was much less clear whether the comparison could be made. The second was that their sample size was much smaller, and in particular they had very few galaxies around between 10 to the 6 and 10 to the 7 in black hole mass. So making claims about the smallest galaxies dominating the volumetric event rate, they say that in their paper, but they don't emphasize it because their sample size is relatively small. So I would say the 2 primary differences are that we have a significantly larger sample size, particularly for small galaxies, and we try to vary as many assumptions as we possibly can. We vary things like the present-day mass function of the stars, the galaxy scaling relations that we use, the surface brightness profiles, which are really an ad hoc choice anyway, we look at different parameterizations, and we find that ultimately our results aren't sensitive to most of these assumptions.
Intermediate mass black holes exist, how often would they disrupt structure?
So if IMDHs exist in the centers of dwarf galaxies, and if dwarf galaxies have the cuspy density profiles seen in somewhat larger galaxies, then these IMDH disruptions totally dominate the volumetric event rate. They may not dominate the observable event rate because they would preferentially, these disruptions would have pericenters at many gravitational radii. So if circularization efficiency is strongly tied to that ratio, then these disruptions might be hard to observe despite their large number.
So I guess I'm confused by your calculation of the rate, because by construction, your two-body relaxation rate is supposed to be a lower limit for tidal disruption. There are other processes that can raise disruption rate in an individual galaxy, like orders of magnitude. So I guess I don't quite understand. Now you're really saying that the two-body relaxation rate cannot explain the problem. If you're not saying that there cannot be other processes that, say, triaxiality, merger, anything like that.
Yeah, that's absolutely true. So the only hypothesis we were trying to constrain by looking at this nearby E plus A galaxy was whether it was so overdense in the center due to its starburst that the two-body relaxation rate alone would be an order of magnitude higher than in a normal galaxy. And the answer to that seems to be no for this particular galaxy. But if the merger created significant nuclear triaxiality or deposited a supermassive black hole binary, then I mean, these are questions we're not addressing. I agree. Those are still very open.